working. Pretty loud. I shouldn't have amped up the volume here, probably. Okay. All right. Well, I want to talk about dynamic scattering some more today, and then there's two techniques related to that: quasi-elastic neutron or inelastic neutron scattering, and then inelastic X-ray scattering. There's two guys in the chemical engineering department that are joint with materials, I guess, or whatever they call it. The kind of part of materials. I thought I'd have them talk too this week, you know. So John Nichols does like kind of biological stuff. Who are you working with? Oh, Euro. Oh, okay. All right. So someone's working with Yavit though, right?
Oh, that's a Beaucage.
Yeah, okay. So anyway, Yavit does this stuff too. Except he does with X-rays. So I asked Yavit, he hasn't replied yet, but Nichols said he'd come in on Wednesday and talk about neutron stuff. You know, so I thought that would be pretty good. But it'd be good if we could get people to show up. Like, so I'm gonna have to send out an email appeal for people to come in, you know, instead of Zoom or whatever.
And I have it. It's I think he majors in neurology, right?
Yavit, yeah. But he does this inelastic X-ray scattering, synchrotron. So you can talk about that, I think. In fact, there's a paper, I have a paper that maybe we'll use that paper this week, you know, for the homework. So maybe you can just talk about that paper on Friday and then get from the horse's mouth. If it looks like that isn't enough, maybe I'll make a little, it should be enough, but if it isn't, I'll make a little recording of like whatever, you know, of like hints on the homework, whatever. So anyway, so yeah, so two classes, hopefully we can get more people to show up for that. Anyway, that's the thing, that's the idea this week. So you know, they're both, well, Nichols been around a little while, but like 5-6 years. So but yeah, it's brand new, so it's good to kind of see these people, I think. Nichols doesn't exactly, he does like bio membranes and stuff. So, but he does this inelastic. So let's see. All right, so you guys can hear me right on the recording?
Yes, Professor.
Thanks. All right, so oh yeah, Shmita, you work for John Nichols, right?
Yes, Professor.
Okay. Yeah, he's going to come in and talk about maybe the stuff you're doing. I don't know.
Okay, great.
Anyway, it would be good if we can get people to come in, you know, for class to have a live, because he's going to give a live talk. So having a live thing would be good. Anyways,
Class.
What?
During the Wednesday's class.
When? Yeah,
So
Wednesday.
Yeah, it's coming during Wednesday class.
When is he what?
See, you said someone is coming during the Wednesday class, right?
Yeah, Wednesday. Yeah, Nichols. Yeah, and then I'm trying to get Yavit to come on Friday. So you have like two guys come in this week, like to talk about these inelastic things. I mean, I've never done inelastic measurements. I kind of know what they are, but they've been doing them. That's the whole thing they do. So, you know, it'd be good to kind of hear from them, I think. So anyway, it's all stuff that's done at big research centers, you know, like let's see, I get pictures of some of these things. Not that, not this. It's like that's the new synchrotron they built in Brookhaven. So it's kind of near New York City. It's on Long Island, near New York City. So that's one place. That's where Yavit's worked some. And then this is Oak Ridge, Tennessee. They have two neutron sources there. One's a big reactor, like a 65 megawatt reactor. which is almost like a power reactor. It's big, like usually research reactors like 10 megawatt, like the NIST one's 10 megawatt. This one's like 7 times bigger than that. Yeah. So it's, but anyway, they have a reactor, neutron reactor there, and this is a spallation place. This cost $1 billion to build this thing. Yeah, it's a lot of money. So anyway, so I'll talk about that at the end here, but basically so Nichols works here. He does a lot of stuff here, and Yavit does stuff here. And you can see they're big things. So this is like $1 billion. You might ask him how much, and how much money he's made from that, so it's just like and then this thing has, so that neutron facility has probably like 10 instruments, I guess, in it. And then this thing is about, like, if you go around this, it's a mile around it, the diameter is like a quarter, half a mile or something. So it's pretty, you can see the cars. Anyway, so this thing will have like so when a charged particle goes around, it changes direction, it gives off X-rays. It's like an X-ray tube. You have an electron, you have a filament, and then a high voltage drop. The faster it's moving, the more X-rays it gives off. And it just flies and stops. So that's a change of momentum. So the energy is converted to X-rays. So whenever a charged particle changes direction or changes momentum, it gives off X-rays. And it's got kind of a Maxwell's law thing, like it'll go kind of in the direction, I guess, like normal to where it stops, it's shooting off X-rays. So in an X-ray tube, it's like at 10 degrees off this plane of the surface of it. If you hit it into copper to get 1.54 angstrom K alpha radiation, and it stops there, and then it gives off at like 10 degrees, because in the plane it absorbs in. So there's like an optimum angle that comes off. And this thing, it's going around in a circle, so it's changing momentum all the time. So there's big magnets that are guiding either a positron or an electron around in a circle, and it's giving off X-rays like the whole time it's going around the circle, right? Because it's going with a high energy. So like 100 kilo electron, 100,000 kilo electron volts or something. No, 100,000 electron volts or 100 kilo electron volts, right? So it's big energy particles flying around in a circle. Whenever they change direction, they're giving off X-rays, basically normal to the circle, right? So there's a beam coming off. But if you want to enhance that, then you put in wigglers, which means that the beam's going through the circle, and at the same time you have it go through this kind of racetrack of magnets where it does this wiggling. So it's really changed momentum a lot. And this is going to give off, every time it wiggles, it gives off a really strong X-ray beam, so then it's monochromatic, because if you design these magnets right, it'll give off monochromatic radiation. So this thing, a wiggler inside a synchrotron, is almost like an X-ray laser kind of, where it's monochromatic, collimated. It's not super monochromatic, it's not super collimated, but it's better than X-ray tube, which is just like white radiation, basically. So anyway, so there's devices like that. And then in this thing, well, if you have a reactor, it's coming off, it's got kind of a Gaussian peak for the energy of the neutrons. The neutrons are particles, so they have mass, so they have a velocity associated with their energy. They're just like ping pong balls. So the faster it goes, the more energy it has. Right. So generally it's in a nuclear reactor, it's too hot, like they're too much energy. You want to have like kind of like something that would have a wavelength of like an angstrom, something like X-rays. So because nothing that you need this subatomic to look at, right? You're looking at crystals and things. So basically an angstrom is a pretty good size scale to look at. So they moderate it with water. So they take the stuff that comes out of the reactor, and they just basically poke a hole in the wall of the reactor. And then usually you'll have like water to moderate it down, to cool it down, basically. So the water will absorb the high energy ones, and you get the lower energy ones. And then if you're doing something like inelastic, you need monochromatic to see the spread of the energy. So they have this thing called a chopper, right? So the neutrons, their energy is related to their velocity. If you spin this chopper at a certain velocity, there'll be a window open for certain energy neutrons to fly through. See, it's like a vein thing. So as it spins, so say you're going and this thing's spinning at 10 miles an hour and you're going 10 miles an hour, then that hole will be able to follow that path straight through. If it's going 11 miles an hour, it'll hit the wall. So this thing's made out of like beryllium or something, or cadmium, I guess, that absorbs neutrons. Absorbs neutrons is a funny thing, you know, because the way that neutrons are absorbed is that it activates the nucleus of the material. So anytime you have neutron absorption, you end up with a radioactive thing, right? So this chopper thing is going to become pretty, if it's running all the time, it's going to get to be pretty hot. You know, so there's kind of weird things about neutrons. Like neutron itself, it'll just fly right through your hand and won't do anything to you. X-rays will it's ionizing radiation, will ionize you and cause cancer, right? So, and the higher the energy of the X-ray, the worse. So because it penetrates deeper and it can ionize like bones instead of skin, you know, or things like that. So neutrons don't do anything to you, but if you have like metals, like iron in your blood or something, then it turns that stuff into radioactive iron 55. And then you have iron 55 in your blood. So that it's the secondary things that get you with neutrons. The neutron itself has no effect. It's got, because it has no charge on it, so it just flies right through you, and it's a subatomic particle. So it's so small, there's a lot of holes in you, and it can just go right through. Never hits anything usually. So anyway, neutron absorption is kind of a funny thing. You're going to end up with a chopper that's pretty highly radioactive after using this for a little while. So everything, all the metals will get to become like radioactive, you know. That's the downside to neutrons. So it's not necessarily the thing that the beam itself that matters. It's like what the beam hit, you know, and then the light, like the radioactive lifetime of the things that it hit are the things you need to worry about. But so you can get monochromatics. You can do kind of spectral analysis of the beam that comes out and say what energy was transferred, like almost like a spectrum that you get. That's one way to do it. And the other way is spin echo, which involves like neutrons can be polarized. So the neutron has like an NMR, the neutron has a spin to it. So, and it creates a magnetic field with the spin. And then the magnetic field, if you apply a magnetic field, it can make that spin tilt. It's got like a director to it. And then that'll precess around in a circle. And so neutron, as it's flying down a tube from the reactor, you can apply a magnetic field to it and orient the spin in one direction. So it can kind of polarize the neutrons in terms of their spin. It's not polarized light, but it's polarized the spin of the neutrons. Then you can pass it through your sample, and then you can unspin, undo the polarization that you did, and the amount of energy that it absorbed. So as it's passing through the sample, it's processing, and if it absorbs energy in the sample, the precession changes. And then when you depolarizes it, the only material that'll go through will be like the stuff that had absorbed energy, and from the amount that comes out, you can tell the energy that was absorbed in the process. So it's pretty complicated. A lot of the neutron stuff gets to be pretty dicey. That's why it's better if Nichols kind of talks about it a little bit. And going through applications is the way to go, because it's too, like, what is a nuclear spin? Like, that would take a long time to figure out. You know, so anyway, so these are all related to dynamic light scattering, right? Because in the beginning, so 1965 probably, they didn't, right after they invented lasers, like when lasers became like available widely, then people realized like this speckle pattern thing, right? That you could have this kind of spots moving, and then they also realized that well, they never had really monochromatic light before. Like you could use a tungsten filament and then put it through prisms or through a grating and then get kind of a single wavelength out of it. So you could do light scattering that way, but you couldn't really get monochromatic light, and you couldn't get coherent light except from the sun, because the sun is so far away from us that the light, all the incoherent stuff has destroyed itself. So all the waves coming from the light are all in phase with each other. Right, so they're coherent. They have a large coherence length. So sunlight you could do coherent scattering with, but you couldn't, and you could run that through prisms and get monochromatic coherent light. So it's possible to do it, but the intensity you could get by that point is like nothing, right? So they didn't have bright, coherent, monochromatic light, right? So it came, you couldn't really do anything like quasi-elastic or dynamic light scattering and quasi-elastic. So anyway, it took the invention of the laser to get this stuff, to get these techniques. So basically, you can either take advantage of the speckle pattern. So that isn't the first thing they did. The first thing they did was just say monochromatic coherent beam goes through a sample, and then it exchanges energy with the particles that are moving around, and that causes the wavelength to shift. Right. So, but the amount of energy is pretty small compared to the energy of the light. So that this kind of approach, even though it seems logical, and that approach is what's used with neutrons and X-rays. This kind of energy absorption, and look at the wavelength shift. So you get something like this. Like you get this is the energy of the neutron or the X-ray, and it's got a peak in it that's pretty sharp. And then after it goes through the sample, it broadens out because of the Doppler effect. Like the material that it's passing through absorbs some of the energy, and if the particles going in the same direction, it adds energy. So it can add or detract from the energy. So it just leads to this kind of Gaussian hump. And then you can have quantized things. So like Raman scattering. So you can have a quantized vibration of a molecule that's a fixed energy, right? So that's different than this. So this thing, you're looking at this kind of broad hump thing, which could be fit with a single exponential decay function to get like a relaxation time kind of thing. And these things are quantized, or fixed energy difference between the energy you had, energy here. That's the quantized energy of a quantum transition, like a vibrational molecular transition. So this is not this kind of quasi-elastic stuff that we're talking about. This is inelastic, like phonon vibrations or something. They're quantized, so they're fixed peaks. That's like a Raman scattering is like that too. So basically we're not looking at those, we're looking at these things like, oh, is water absorbed to a membrane? So water is running around, and then when it gets absorbed to the membrane, it can't absorb as much energy. So this vibrational energy changes, and the fractions of water that are absorbed and not absorbed, you can tell from this. There's no other way to tell that. Like there's no other way to really measure that. You can simulate it in the computer, but this is the only way to tell, in this week's thing with the little ball bearing lubrication things, like did the water actually absorb into it? Well, they do a DSC and they see that peak, but the peak could be from something else. This tells you that actually the water actually is fixed inside the structure, like it stops moving, right? So it's pretty useful, and then people gravitate to it because it's a $1 billion machine. There's only, around that $1 billion machine, there's only 10 instruments. So it's like $100 million for that one instrument. And you get it and these experiments take a long time. So you get that $100 million instrument for like 2 weeks. So whatever that comes out to, it's a load of money. It's plenty to buy like whatever kind of electric car you want to get, a Tesla, that sports car thing. So you get that. Anyway, or you could do this experiment. It's your choice. But not many people would take the experiment. But still, it's got a little bit of profile to it because of that, right? So on the other hand, these synchrotrons, first off, there aren't that many neutron places because no one wants to build a nuclear reactor anymore. So in the 50s and 60s, like everyone wanted a nuclear reactor in the backyard. And Oak Ridge, because Oak Ridge already had, so the first reactors were built, the first reactor was built in Chicago, University of Chicago, under the football stadium. Then Argonne kind of took that stuff and built a bunch of reactors outside Chicago. So like maybe half an hour from downtown. And then Oak Ridge, they wanted to make an atom bomb once they realized that you could do that. So Oak Ridge became the center because it's far enough from the coast that a bomber from Germany or something couldn't reach it. And then for the same reason, Oppenheimer picked like Los Alamos, which is in the mountains in New Mexico. It's really hard to reach for bombers. So they found these places where they thought they could do this stuff, and Oak Ridge became a place to like enrich uranium. Kind of what the Iranians are doing now that we're trying to stop them from doing. We did that in Oak Ridge, you know, so this big, you do it with a centrifuge, you separate by density because so Oak Ridge was that. And then it became, because they had the isotopes there, it became the center for reactor development. It's like all there's you drive through the Oak Ridge lab, there's like almost like a reactor Disneyland or something. Like every kind of reactor, liquid sodium cooled, all kinds of different breeder reactors. Most of them are retired now, but because they're radioactive, like they're just sitting there as like monuments almost, you know. So it's like you drive through a graveyard of nuclear reactors. And Heifer, the 65 megawatt reactor is one of those. You know, it's down in kind of a valley. So there's a lot of radiation in Oak Ridge. You know, it's in the water and stuff. So they have it kind of fenced off. One side you can hunt deer, the other side you can't. There's a fence. One side is legal, that they hunt deer there. No problem, hunt them. On the other side of the fence, the deer are radioactive. Right. The same with the fish and everything. So it's kind of a funny place. They had people parked, like the parking lot wasn't big enough for this reactor. So people would park on the road under the trees. And a guy had a rental car, right? And then they have badges that you wear to go in because it's kind of radioactive. So the guy took the badge out and took the rental car and drove back to the hotel, came back. You're supposed to leave the badge at the reactor, not bring it with you. It came back, it was like lit up, like something went on. So they found out that it was because the leaves from the tree fell onto the car. And those leaves were like radioactive because the soil is radioactive. So all the birds in the trees, it's a big problem. You know, the radiation is kind of a serious thing. You can't just mess around with it. But they bought the car, they made it no parking in that area. They cut down a couple trees and they built a bigger parking lot. That's how they cope with it. They also have kind of barrels.
What's the radius of the radiation?
The radius?
Yeah.
You mean what? I'm saying like how far can a bird fly? If the tree is radioactive and the bird lives in the tree, okay.
Yeah.
I mean, you know, same with the fish and the deer top the fence, you know. So I mean, so you got a little glow in the dark deer hopping around. It's a big problem when if you have a big facility, you know. So they turned out an industrial scale, you know, like to make nuclear bombs. Then they also got into the business for reactors too, but they don't do that now. That's done in like Paducah, Kentucky, and there's a couple other places. It's like where the Mississippi and Ohio cross. That's a lot of the nuclear fuels coming from. It's a big swamp. So I don't know. I don't have answers to these things, but basically you got to realize weird things happen that at the time they didn't know, you know, but then they knew eventually, like they learned because people were dying, you know, so, but anyway, it's a big problem. It really is a big problem. Anyway, so Al Gore was from Tennessee, right? And he is anti-nuclear and he ran for president and kind of won, but kind of didn't win, you know, so anyway, when he was vice president under somebody, Carter or someone, I forget.
Yeah.
Jimmy Carter, who's just gone into death thing, right? But anyway, so they were going to build this, and it's $1 billion for Tennessee. Tennessee's kind of poor, you know. I mean, it's in the hills, like I don't know, Smoky Mountains. So he was like, "Yeah, that's great, $1 billion for Tennessee." He was he was vice president then, and then they told him, oh, I mean, so it got all approved by Congress, went through, got to the president's desk. Someone told him, oh, it's a nuclear reactor, you know. So he said, then they nixed it. Like the president didn't sign the bill. It was already approved, $1 billion. And they went back, and then Oak Ridge and the Department of Energy said, oh, well, they can do it with this spallation source, which is like, you see back here, there's a linear accelerator here. See that thing? So that thing just fires. All that thing does is like fire a gun at a piece of metal inside this warehouse thing here. Right, so that whole thing is just like an accelerator to get the energy up enough, I think, for electrons, some kind of particle. It blasts a piece of metal, and from that blasting that metal, radiation, mixed radiation comes off, like all kinds of different. One of the radiations that comes off is neutrons, and it can produce a lot of neutrons. But these accelerators are like a pulse laser. They fire up and then boom, it's literally like a gun, right? So it's going like 60 times a minute, basically 60 hertz, like pounding that metal with these particles. So that means every time a bullet hits the metal, you get mixed radiation neutrons coming out and other things. You know, so the problem is, like, when you get mixed radiation, like in space, it's a huge problem, because if you put up borated polyethylene to block the neutrons, that becomes activated by the neutrons. So then you have X-rays. And if you put up lead for the X-rays, that becomes super activated. That becomes like a 2,000-year lifetime radiation material, you know, and the same like cosmic rays. So if you have mixed radiation, there's no way to shield it. Like, you can shield one of them, but you can't shield all of them, because when you shield one, you produce the other. You know, so it's like, it's kind of a thing you can't. That's why, and also in space, like, it's full of mixed radiation, and you know, you can carry things up like aluminum. Like, you can't carry lead up into space. I mean, it would cost too much. So basically, if you go to space, you're going to get seriously dosed with all kinds of radiation. Not only that, but there's like nano-sized particles that are flying around in space at like millions of miles an hour, right? Cosmic particles, and they're inundating you from all directions, and they also can't be shielded. You know, so basically your spaceship is eroding off, and you're being like dosed with all this stuff to go to Mars. Is nuts. Don't do it. You know. Anyway, so this thing, because it's doing that, is sending off this white radiation that's time, but neutrons within that spectrum of radiation, the neutrons velocity is different, right? So the fast ones the high energy ones fly out fast, the low energy ones are just crawling along. Right, so you need a time selector. So the detection is going to be 60 times a minute or 60 times a second, and then just pick up the time of when it arrives. And that time when it arrives is a wavelength that it was. So you're going to have a detector that picks up every second, picks up a whole spectrum, takes all that data, like many gigabytes of data, and then bins that into time sectors, and then collects it so it's under wavelength. So you can get kind of monochromatic for a bunch of different wavelengths. So Q is 2 pi over wavelength. So basically, you're getting all different Qs from one position with this, as long as you have the computer to figure out how to bin all this stuff. Right, so it's kind of dicey. They had the first one of these was at Argonne. They kind of built it, and it lasted for a while. It took them 20 years to get it to work right. You know, so it always takes a long time to get this kind of setup to work, right? A reactor is much nicer because just one wavelength coming through. Anyway, so that's the spallation thing in a nutshell. This gun firing at a piece of metal, and you're collecting the stuff, and the metal becomes like super highly radioactive. They call it the crypt, like where they keep it. You know, so it's like the instruments are shielded basically, and it's kind of safe to work there. This is the NIST. So right outside DC in Gaithersburg, that's the NCNR Nuclear Center for National Center for Neutron Radiation Research at NIST, right? NCNR. So that you can apply for time there. This is actually, this curve thing is one of their time of flight detectors, I think, to detect quasi-elastic stuff. And the long things are small angle neutron scattering detectors. You can see that's a person here. So it's a pretty big warehouse they built. And the reactor here is way down at the end, and there's a little 10 megawatt reactor that was built in the 1960s that had a lifetime expectancy of, I think, 50 years, which they've extended over and over again, you know. So now it's shut down because of something cracked, something happened. Meanwhile, so it was built in the middle of the field in the 1960s. Now DC has grown out, so it's surrounded by $1 million house developments. So it's like billions of dollars of houses all around it, right up to the fence. And then there's kind of a campus from this, and this is at one end of the campus. So how long until people realize there's a nuclear reactor in your backyard, and if they're rich enough, then they can probably get rid of it. So kind of at this point, it's hard to tell if it makes sense, to have that there, but it's a small reactor though. So it isn't like this kind of 65 megawatt thing in Oak Ridge. Anyway, and then ILL in France is one of the big ones too. It's in Grenoble, so which is kind of the ski country of France, not too far from Switzerland, but so they put these in nice places sometimes. But all right, so anyway, yeah, so originally they had the two ways to do light scattering, and this way died out because the energy change isn't enough to really measure that way. Even though initially without a correlator, the idea of trying to watch the speckle pattern change wasn't really that feasible, right? So until they developed a correlator, which happened in about 5 years after they kind of started doing this stuff, then this became the only way to do it. No one thought about doing this anymore, and then this later was adopted by X-ray and neutron to do the inelastic measurements with neutrons and X-rays. Anyway, so let me just go back up here. So anyway, the whole thing with it, if you're doing this DLS thing, it relies on the correlation function. I think I mentioned that before. So there's a lot of uses for these things, like even kind of just mixing, looking at mixing of things. So you can say like the speckles, and I'm going to say like if I have a distance r, and then what's the likelihood of finding black at 2 r points. So you do an integration of that. Let's see, I guess this is the equation here. See, it should be a double sum, like 0.1, 0.2, and you have sum over all possible 0.1s and all possible 0.2s that are separated by some distance. This distance r here. So you have 0.1 is x1, 0.2 is x2. It's just like, is it black or not? And then this is the mean. So you multiply those two, that gives you the correlation function. You can normalize it by the average. This S is the average of the deviation from the mean squared, because this is going to end up being squared, so it has to be squared. So if this was the mean minus the mean, it would be 0, but because it's a difference squared, this gives you like the standard deviation kind of. So you normalize by the variance. So you normalize by the variance. You get this correlation function, and then these are correlation functions for if you have a equally spaced stripes, or if you have a checkerboard. So the correlation functions are almost the same. So when you do this correlation function, something's missing. Like you get an idea about how the black dots are correlated, but you don't get you can't recreate the black dots again. Like the stripe and the checkerboard are almost the same correlation function, right? So that means that you can't say, is it a stripe or is it a checkerboard? You can only say that the black and whites are separated kind of by some distance difference, and that the density, like what is the density of the stuff, the density of the black and white. So correlation function doesn't answer all your questions, right? You can only answer certain questions. So you can talk about the scale of segregation, which is the integral of that thing, dr, right? So you end up with a size scale, and that ends up being basically what's the separation distance between the black dots and the thing. So, I mean, here you can see what the separation distance is. If you have something like that, it's not so clear like what it is. So if you have some messy system, whatever, this is going to be something that's kind of useful. Kind of gives you the mean free path between the things. So there's limitations to the correlation function, but it's useful to recreate things. The bottom one is from a real, like one of these extruded films. And then what's the correlation function look like? So you end up with kind of a decay function, which will give you, that decay function will also give you a characteristic size if you fit it. And so anyway, so it depends. So there's limits to what you can do in this. Like, in other words, if this is time instead of space, so there's the longest time you want to spend taking data. Like how long are you going to sit there running your sample? And then there's at the low end, it's a resolution of your instrument. Like how fast can you take a data point? Or in this case, like what kind of microscope are you using? What's the resolution of it? Like a micron or something, right? Or 10 micron. So basically there's two limits to these correlation functions. One's instrumental and one's kind of what lengths are you willing to go to do this measurement? You know, like, are you going to measure to Mars to figure out like what the correlation function is? Or so anyway, this is an example. Forget where this is from. I guess it must be from Wikipedia or something, but it's a damped sine wave, right? So you have oscillations and it's damped out. And then if you take that sine wave and you say, I'm going to use that as a weighting factor to put these points in randomly. So I'm going to randomly put my points in according to that decaying sine function. That's the signal I would get from it. Right. So if you look at a time signal or a frequency signal, the things can look quite a bit different. So in the frequency signal, you're looking at what's the possibility if I have this signal, I'm going to find this same signal somewhere else at a time difference delta t, right? And when you get to 0 time difference, it's 100% because then it's going to be the same as what it was. So it always goes to 1 over here at the 0 point. And then at long distances, it's going to be the average value, right? In other words, the odds, if I'm at one end here and I go so far away, and I move that thing around, I'm going to end up with just the average over. It doesn't matter about the first point at that point, just the average of all the things. So your final value should be the average. So usually subtract off the average from the correlation functions. This goes to 0. I mean, you'd subtract off the average one because that's trivial. Like you already know that maybe. So that's the kind of idea. So correlation functions you use all over the place. That's the point of this. Then, so this just shows like an intensity versus time. So you shoot through the sample and then you pick up with a detector at some q. So 2 pi over lambda sine of this angle, right, will give me q, and that's going to be 2 pi over the d spacing, or 4 pi over lambda sine theta, half of theta will give me the q, and 2 pi over q gives me the d spacing of this thing. So the d spacing is the size scale that you're observing at this intensity at that angle. So 2 pi over q gives you the size scale, and then this is the time dependence, and the time dependence. So at short times, it's going to be 100% correlated. At long times, it'll be the average. In between, there's a decay function. It's going to have a decay function that describes this correlation length. So if it's following Brownian motion, then you're going to have that the mean square displacement goes with 2 diffusion constant times time. The time is this tau, like the relaxation time for that decay, and the distance is going to be 1 over q, so 1 over q squared. So tau is going to be 1 over q squared, 2 times 1 over 2 qd will be tau. So that's kind of bulky. So they have this gamma that's used. So you just use gammas 1 over tau is q squared d. This should be a 2 in front of it. But so basically that's what governs this correlation function. So if you want to, if you measure the intensity at a certain q, and there's a delta t, you get the average. That gives you this G2. It's G2 because it has still this mean in it, the mean value. Like at long distance, it's going to go to the mean value. So you want to subtract that off. So you have the mean value. So this G2 is the mean value times 1. And then some other number times this G1, which is a decay function for the noise pattern. Right? Like this, if this is based, where the average is 0 here, so you have to subtract off. That's why this becomes a little dicey. Like it's got, so they have like capital G2 isn't normalized, small G1 is normalized. And then so this is how it fits together, but you don't need to know that because the correlator and the computer just give you G1. Like it just spits that out. And if you're going to do this, you're going to use a computer. And no one really knows how a correlator works. It's one of the instruments. It's really a black box. You just have to trust it. there's no way to figure out how a correlator works. Right? It's a hardwired device that calculates this G1 basically. So I think you don't really need to know that G2 exists, and just say you have this G1 that comes out, and there's this decay function that it follows. Right? And the size scale you're measuring that is Q, so 2 pi over that is going to be the size of the thing. Anyway, these are then the machine will spit out different kinds of plots. Again, this is from Paul Russo's slides. So this hydrodynamic radius, people like it because it's easy to measure, and it works great for spheres because that's the radius of the sphere. And it's doing the dynamics of it, so it doesn't know anything about the internal structure. So if it's a bubble, it's still the radius of the bubble. And anything within the sphere it can't see because it only sees the drag coefficient. So it's just the radius of it. If it's some other shape, then it's complicated what RH is. So it's an equivalent sphere for a cylinder, for a cube, right? So you don't exactly have a mathematical. There's this equation that will give you can calculate, but oh, where is that? It's at the beginning here. Sorry. So we can use this Kirkwood equation to calculate for odd objects to get the hydrodynamic radius. But again, it's going to depend on how draining, is it draining or non-draining? So if it's a Zim model, then it's not draining, then the polymer coils a sphere. If it's totally draining, then it's this equation to calculate RH, and they're going to be different numbers. Right, so depending on how much the solvent stuck in the thing, that's why he says here that all bets are off. Like for object is some other shape. So all bets are off. So basically, you kind of have to make some assumptions and say what RH means. So the nice thing about this machine is you can stick anything in it. So this is just stick milk in it, right? And do backscattering, usually if you're doing something that's turbid. And it'll give you the size of so milk is basically colloidal spheres floating around in water, right? And you know the viscosity of water, so you can get the hydrodynamic radius for the things. And it turns out there's different sizes for the colloids in milk, and something that's available is easy to measure in this machine. So I don't know if it's so anyway, you can find papers. People have done their PhD dissertation on milk and dynamic light scattering from milk, believe it or not. So if there are places where dairy is important, so there's stuff you can get out of this, even from milk. So you can imagine paint, anything. People are going to love this machine because it spits out a size. So this is kind of like there's 3 versions of this. So this is my version from, I think the Russo one's better because this thing gets from a book, and it's too complicated actually. It's the same thing. So you can see this could be pretty dicey if you, the same thing. So it's the correlation function for the intensity. And then these are the electric field waves, so light is made up of waves with an electric, so the magnitude, the amplitude of the wave, electromagnetic wave, the dot product of that gives you the intensity, because this is a complex number because it's absorption. So at T or at some other times, this is basically the same thing as what I said before, two different times, multiply, find the average. And then there's just so there's this average value total over all time, and then there's some prefactor that adjusts that. So you can see the math can look more complicated, but it's the same thing that's being talked about. So this is actually a picture from our instrument down in the characterization center, what it reads out, like the noise pattern and the decay function. And then that's the same stuff, right? So there's a wiki page for it. That's about it. So it's basically the same kind of approach is going to be used with X-rays and neutrons. Hopefully Yevit can talk about the X-ray part, and then John Nichols can talk about the neutron part of this, a little bit. And then, so anyway, so there's some other technique that came up in late 90s or early 2000s. I don't remember. There's a guy at University of Pennsylvania that developed this. Anyway, so it's kind of a weird thing. So usually if you're doing this scattering measurement, multiple scattering is a bad thing. Like if you have a sample and you shoot the beam through it, you always want to be able to see the beam on the other side. If you can't, then kind of all bets are off because the beam is going in. Like if you shoot a beam of light through milk, then if you look at the other side, you just see like a halo where the beam was. Collimated beam, it should go straight through and you see a spot, right? But if you don't see a spot, you just see like a halo, then or like a Gaussian kind of blob thing. Then you know that the light hasn't, that probably the light has hit many places in order to make that halo. So it hits one object, scatters off, hits another object, scatters off. So it's following this random walk through the sample, then finally getting back to where you're detecting it, right? Which means there's kind of no way to analyze the data after that. Because you're trying to talk about an angle, and that gives you Bragg's law, that gives you the size. You can't measure an angle from a blob. Like it doesn't have a line that you can detect the angle from. So you just have this blob thing. And then you do get a scattering pattern, but it's kind of like hard to interpret it. Right. So anyway, so that's usually detrimental. So you try to dilute down the sample. And in the DLS, what they do is do backscatter because the beam can only pass so far through, and they assume that you only get a sample that isn't multiple scattering when you take backscattering from it. So it's possible to do DLS on milk in a backscatter mode. Anyway, so dynamic, this diffusive wave spectroscopy, you take a sample and you're not interested in the, you put in a monodispersed sphere into the sample. It's suspended in whatever it is you're looking at. And then you are you looking at the motion of those spheres, and you want to have it like in the multiple scattering regime to do this. See, so you can either do backscatter or transmission with this thing. So basically, if you look at the like a spectrum from some kind of polymer, so you have the storage modulus goes up. There's a crossover frequency that's relaxation time for the material. It's liquid on this side. That's loss modulus, and then loss modulus goes down. But there's a problem when you go to high frequency in one of these rheometers like this thing. So the problem is you get kind of slip at the wall. So if you get this thing spinning fast enough or oscillating fast enough, the assumption of that machine is that the liquid is stuck at the wall and it's stuck at the spindle or whatever is in it. So the thing is spinning and the wall, liquid is dead there. So you get a gradient across it of the velocity. So you have the spindle motion and the wall is fixed. So you have a linear velocity gradient across it. If it slips at the wall, then all bets are off. It doesn't work anymore, right? So at high frequency, you get more of this slip with the wall. And basically you can only measure up to a certain frequency with a mechanical viscometer, right? So people looked at different kinds of viscometers to overcome this. So you get to really high frequency because there's a lot of information here for polymers. Like this becomes linear again. So you get kind of local flow when you get to really small sizes, and small sizes you see at high frequency, like a small bill is a high frequency bill, high pitch, right? So if you want to see inside, say you have a network of entangled chains, you want to see the motion within those tubes, you need to go out here, and you can't measure that with that mechanical viscometer. So you need something else. One way, I mean, in the old days, they had a ball, a magnetic ball that you would put in, and you could spin the ball within the fluid, right? So the ball was like a probe. So you can use Stokes' law on a ball, and then you can figure out the drag coefficient, and that you can get the viscosity, right? So you have the ball in the fluid, it's spinning with a magnetic field, and you can figure out by how fast it spins what the viscosity of the fluid is, and from that you can translate it into this storage and loss modulus, and you can get kind of higher frequency that way. So this guy at Penn, who I forget his name, I think it's Weiss or something, I think is his name. He figured out that you could fill the fluid with beads. So this is called, that's one type of microreology is putting a bead in that's magnetic and spinning it, and then watching it move. Another type, so that's called an active microreology. This is passive microreology, so it lets the beads move with diffusion, Brownian motion, right? So they're moving around with Brownian motion. If they're moving with Brownian motion, you can get the diffusion coefficient, and that's going to give you the viscosity, basically the fluid that the bead is in, right? Because you know the radius of the sphere, so you know the hydrodynamic radius for the spheres. You don't know the viscosity of the fluid at high frequency. So you get the viscosity from the dynamics from the DLS of these beads that you put in as a probe for the thing, right? So you stuff in beads and you watch that motion. Then this is showing like, so basically there's two kinds of motions that beads can have. They can have viscous or Brownian motion, which is the mean square displacement goes with time linearly proportional. So you can see it goes 1 decade, 1 decade. Right, so it's power 1. Or you can see elastic motion where the thing plateaus out. So if it's elastic, this is just a fixed mean square displacement with time. Time doesn't matter. It's a solid. So you can get both of those kinds of motions from this bead Brownian motion thing. This is Brownian motion. This is elastic motion. It doesn't move, right? And this does move. So because of that, you can get G double prime would be the Brownian part, and G prime, the storage modulus, would be this part. And from analyzing the motion of those beads through a DLS measurement, you can basically get the rest of the curve. You can get the rest of this curve. You can get the blue lines from this thing, and they match up pretty well with the red dots that were measured mechanically. I mean, it's not exact, but basically they're pretty close. So you can combine these curves. So we're doing something like simulations of polymer flow, like this becomes really useful because simulation of a polymer flow starts from the bottom, it starts from here, and then goes over here to predict the stuff you see in an extruder, right? So see, if you can't see this part, then all this is guesswork. Then oh, it worked, you know. So it's kind of like, it doesn't always work. We don't know why. So why is because like what happened initially at the small scale. So if you can't verify your models at this scale with some technique, then you can't really predict over here where you really want the data, right? So anyway, so this is an instrument you can buy now. I mean, it was originally just available to the one guy, and then basically it became commercial. So you can buy this machine. I think it's like 20 grand or something. It's not much for instrument wise, you know. So you can buy this diffusive wave spectroscopy machine. There's a bunch of people doing work with probe, like this kind of microreology, doing different things with it. So it's actually a field. There's probably, I don't know, in the US, there's probably like 50 people doing micro, maybe 100, I don't know, like professors, you know, doing microreology stuff, various things. A lot of it is biological, like looking at how proteins stick to something, or because it's easy to do. It's pretty easy to use a DLS to just kind of mess around with the thing. The mathematics of it, and not really going into, you know, but basically it's going to be this. So this is called a Laplace transform. It looks like if you put an I here, this would be a Fourier transform, right? So Fourier transform saying because e to the I is like a sine wave, sine plus I cosine. So that means you're applying to your signal, you're decomposing your time signal into a bunch of sines and cosines, and then you get your amplitude signal in Q. S is basically Q, it's an inverse space, or inverse time here is like a frequency. So anyway, this thing does something different. It's not applying sine waves, it's applying exponential decays. So the same kind of decay, like the same decay that we had here. Like we say, it's an exponential decay of the motion of the thing someplace, like this thing. So it's an exponential decay. It's this kind of knee thing in a log-log plot or log linear plot. So it's basically, that's a one-time constant thing. So you say your system's made up of a whole bunch of one-time constant things, and the amplitude of those one-time constant things are going to be this signal. So this is your raw signal. It's composed of these things. And then this is your amplitude signal for all the time constant things. And that thing's, so anyway, that's how this Laplace transforms how how you look at this data from this machine and you finally get G prime, G double prime out of it through a bunch of math. That's kind of complicated. This is some of it, but basically, I think you won't be able to decipher what's going on here. Anyways, but you can get this curve in the end. You can get the blue lines from that machine. So it's pretty useful. All right, so that's about it, and we're out of time. So hopefully John Nichols will be here and we can kind of go through some of the neutron stuff on Wednesday. Any questions on the homework or anything? All right, so email me if you got problems with it.
Okay.
So. All righty. It's like a rainy day today. It was a nice day